Now let's run through a few quick examples of applying the various properties of definite integrals. You might find it useful to pull up that page from the ebook or from your notes if you have copied them down so that you can reference them as we go. Let's start with this one that asks us, given that this integral is equal to 5 radical 5 minus 8, what is the value of this integral? So let's copy this thing down that we have. This is the integral from 1 to 0 of 3u times the square root of u squared plus 4 du. And we're asked to figure out its value given information about this integral. This is the integral from 0 to 1 of 3x times the square root of x squared plus 4 dx. So if we look at this, we want to find all of these similarities and differences. So starting off right off the bat, we look at the bounds on the integral. We have one that goes from 1 to 0. What we were given goes from 0 to 1. Those aren't the same, but they are the same numbers at least, so that looks related. We have 3u times the square root of u squared plus 4 du. This is 3x times the square root of x squared plus 4 dx. This is exactly the same structure, just with a different variable. Now, our choice of variable doesn't matter. This is basically just what are we labeling the horizontal axis as, right? You can call that whatever you want, and this evaluation, this area being described here, is going to come out the same. So the first thing we can do is rewrite our integral, but just swap out the variable. You can pick any variable you want. Here we have u. We can change this to literally any variable we choose, but of course the smartest one is x, since we're given that information here. Fix that weird looking radical. There we go. So now this is almost there. This almost perfectly matches. The difference now is just that order of the bounds, right? We were given an integral from 0 to 1. We have one from 1 to 0. But looking over your integral properties, if you have an integral from left to right and an integral evaluated from right to left, these have opposite values, because what we're basically just doing is switching the signs of all the delta x's, or dx's, depending on how you're... If you take the dx and you translate it to a Riemann sum, you have delta x's, and those would switch sign. So this integral that we have is the negative of the integral from 0 to 1. We have the integral from 1 to 0. That is the negative of the integral from 0 to 1. When you switch the bounds, you negate the value of the integral. So we have 3x times the square root of x squared plus 4 dx. We are told what this integral is equal to. That is 5 radical 5 minus 8. So we have the negative of 5 radical 5 minus 8, and that will be 8 minus 5 radical 5. So there's a certain sense in which we're kind of just playing around with symbols a little bit, use a couple of properties and switch things around. There's another sense in which there are, intuitive meanings behind all of this. So we're kind of abstracting a structure and using some characteristics there. But this is a fairly simple example of just applying a couple of integral properties. Let's look at another one. We are told that the integral from 1 to 5 of f of x dx equals 12, and the integral from 4 to 5 of f of x dx equals 3.6, and asked to find the integral from 1 to 4 of f of x dx. Notice that we're never told what the function f is. There's just some function, which is apparently integrable because it has values over these intervals here, and we're asked to find the value of another integral. There are a few different ways we could organize this. They're all basically equivalent, but kind of invoking different properties and taking different approaches. I'm going to go through 2 of them to work out a couple of different properties, and you can see how we can apply those. So one of these, so we notice that the integrand and differential are the same in each case. F of x dx, f of x dx, f of x dx. There's none of that changing variables business like the previous example. So let's focus on the bounds. We have 1 to 5, 4 to 5, and 1 to 4. Now, remember that there is a property that allows us to kind of paste integrals together one after the other. We have an integral from 1 to 4 and an integral from 1 to 5. So if we write the integral from 1 to 4 of f of x dx, and we add to that the integral from 4 to 5 of f of x dx, that will equal, so we're summing up, we're finding the area from 1 to 4, then we're adding the sum from 4 to 5, we're just picking up where we left off. This is just the integral from 1 to 5 of f of x dx, right? So we have the integral from 1 to 4 of f of x dx. That is our unknown. We don't know what that is, so I'll just recopy that as it is. The integral from 4 to 5 of f of x dx, we were told is equal to 3.6. And the integral from 1 to 5 of f of x dx, we were told is equal to 12. So that means then, of course, a tiny bit of trivial algebra, the unknown that we were asked to solve for is equal to 12 minus 3.6, which I guess is 8.4, if I'm thinking about that correctly. Hopefully. Something like that. You get the idea. Okay. So that's one way we could do this. Another approach would be to kind of set this up with, let me do this. We can take our given information and sort of set it up to force it to be equal to this stuff, right? So we have the integral from 1 to 5 of f of x dx, and the integral from 4 to 5 of f of x dx, and we want to get the integral from 1 to 4, right? Well, this integral from 4 to 5 is the negative of the integral from 5 to 4. So if we wrote the integral from 1 to 5 of f of x dx plus the negative of the integral from 5 to 4, it's maybe not the best way to do that. Let me back this up. I think the easiest way to write it would be to say, okay, suppose we take the integral from 1 to 5 and add the integral from 5 to 4. I think that'll be a little bit of an easier way to express this. I changed my mind midstream. It was getting a little bit messy. If we just write this, the integral from 1 to 5 of f of x dx plus the integral from 5 to 4 of f of x dx, just formally, going from like a to b and then b to c, that would be the integral from a to c. So the integral from 1 to 4 of f of x dx. Intuitively, what's happening here is we're starting at 1, we're going right to 5, and then we're adding the bit that goes from 5 backward to 4. And when we do all of that and then come back, that'll leave us with just this part. Because remember, going backwards is negative, so we're going to subtract that off anyway. So if we write this expression, then it'll equal this thing. Now we don't have the integral from 5 to 4, but we do have the integral from 4 to 5. So I can write this as the integral from 1 to 5 of f of x dx plus the negative of the integral from 4 to 5 of f of x dx and now we can plug in these things that we know, right? We were told that this is 12. We were told that this is 3.6. And then simplifying, we again get our 8.4. So that's using some slightly different bookkeeping, including that switching around of the bounds there. As we're doing manipulations with integrals, we do sometimes have choices as to which properties we want to invoke and or in what order we choose to do so. For the last example, we are asked to use property 8 to estimate the value of the integral from 0 to 2 of 1 over 1 plus x squared dx. Now, I've reproduced property 8 here, so we know what we're talking about. If small m is less than or equal to f of x, which is less than or equal to big M, for a less than or equal to x less than or equal to b, then small m times b minus a is less than or equal to the integral from a to b of f of x dx, which is less than or equal to big M of b minus a. Now, that might just be a mess of symbols in algebra, might not mean a whole lot. Let's kind of unpack this. We have this integral here, the integral from a to b of f of x dx. So we compare that to the integral that we have here, right? The idea is we have some function that we're integrating. You can think of that as finding an area under the curve. A and b are the endpoints. In our specific example, we're going from 0 to 2. We see that here we have a less than or equal to x less than or equal to b. This just means that x is within the interval, right? This is the interval from 0 to 2. So as long as x is within that interval, we have this property. So we're basically saying we have small m and big M as being constants that bound our function below and above. So our function is constrained within these two numbers on this interval. If that's true, then the integral is bounded between these two values. Now, these are the lower and upper bounds, each multiplied by b minus a. That's just the length of the interval here. So let me kind of sketch out what we're looking at. We have, let's see here, how do I want to do this? Just drop down some axes. Let's make this 1, and we'll make this 2. So let's graph this function. F of x is equal to 1 over 1 plus x squared. So when x equals 0, we have 1 over 1, so we have this point here. When x equals 2, 2 squared is 4, plus 1 is 5, so we get 1/5. So we get this value here. That is 1/5. Okay. Now, what does this function do as we go from 0 to 2? Well, if we think about this, we're starting when x equals 0, and this whole thing equals 1. As x increases, x squared increases, which means the denominator increases, which means this fraction decreases. So this is going to drop down from 1 to 1/5. The precise shape isn't too important. If memory serves, it goes something like this. We don't really care about that. The idea is that it does not increase above 1, nor does it drop down below 1/5 on this interval. Now I'm just kind of using some hand-wavy justifications here. If you want, you can address that rigorously by making this an extreme value theorem problem. You know, finding absolute extrema in the early portion of chapter 4. We can say this is our function, here's our interval from 0 to 2. You know, you can take the interval, take the derivative, find the critical points, test those critical points along with the endpoints to find the absolute maximum and absolute minimum on that interval. And we find actually that the maximum is 1, the minimum is 1/5. These are the values of small m and big M. This value of 1 is big M. This value of 1/5 is small m, right? These are upper and lower bounds. We look at what we have then. If we consider the constant functions y equals 1/5 and y equals 1, we see here, if we are trying to find the area under this curve, we can look at a couple of other areas. There's the area of the small little rectangle down here. This has an area where its height is 1/5 and its length is 2. How do I know the length is 2? Because 2 minus 0 is 2. 2 is the right endpoint, 0 is the left endpoint. Those are b and a respectively. And their difference is 2. b minus a, again, is the length of the interval. That should be less than or equal to the integral in question, right? Because you can see this the area that the integral describes is clearly not smaller than this rectangle down here. And that area is also clearly no larger than the big rectangle that we get by taking 1, which is the maximum value, our big M, and multiplying again by the length of the interval. So what we have is that 2/5 is less than or equal to the integral from 0 to 2 of 1 over 1 plus x squared dx, which is less than or equal to 2. Okay. Property 8, if you're not sure what all these things mean, it's just a bunch of algebra. Don't try to memorize these properties, right? There's a whole long list of properties. If you're just trying to memorize them, that's terrible. Make sure that you think about what they represent. Think about things in terms of areas under curves. Keep in mind that the A and the B that keep showing up are the endpoints of the interval, all of that kind of business. And think about what this geometrically and quantitatively represents. I drew a geometric picture here, interpreting this integral as an area. But remember, this integral represents a limit of sums. So you can think of this as a sum of function values multiplied by little values dx. Okay. So if you factor out the dx's, you can think about what the sum is doing. And clearly, if the function is bounded between small m and big M, then if we were to replace the function with small m, we would get a lower bound. And if we replace the function with big M, we get an upper bound. And if you integrate if you have a constant multiplied by those little delta x's, when you add up all of those products, it will be that constant times whatever the sum of the delta x's is. And that is the length of the interval. So that's what we have here. So again, a few quick examples to illustrate the integral properties. Hopefully that helped show how you can think of some of these kind of intuitively or geometrically. And again, keep in mind the underlying structure. This is like the Riemann sums that we dealt with in the previous section. We have a sum of a bunch of function values multiplied by little delta x's or dx's, depending on how we're writing it. But it's this is just a notation for the limit of those sums. And it behaves, in many respects, just like a sum.